what do we get when we combine a French revolutionary with an American miner? If we believe our history books, we get a great chemistry team. This may sound like a joke, but James Craft, an American, and Charles Friedel, a Frenchman, were lifelong friends who developed a lot of great chemistry together throughout their careers. Now, in the 1800s, they were working together in their lab, and they mixed aluminum filings along with amyl chloride, which is a variety of isomers of chlorinated pentane. And what they observed was that there were fumes of hydrochloric acid as well as volatile hydrocarbons that were produced in this violent reaction that occurred between the aluminum and their chloride compound. Now, of course, when you've got fumes of hydrochloric acid, your first instinct might be to flee the lab, which you would be justified in doing, because that is a somewhat dangerous product to be produced in your lab. But back in the day, safety standards weren't quite the same as what they are today, so they actually pursued this reaction further, and they were able to mix together benzene with another chloride-based compound. So they reacted it with aluminum chloride, which they determined to be the reactive component of the aluminum filings and that chloride-based compound. And they added this together with a methyl chloride compound, and they were able to produce toluene. So toluene is our benzene ring with that methyl group substituted onto our ring. And they also produced hydrochloric acid as well, which of course is what produced those toxic hydrochloric acid fumes. Now this reaction is what we call the Friedel-Crafts Alkylation reaction. And it's another example of an electrophilic aromatic substitution reaction, similar to that nitration reaction that we looked at in our previous lecture. Now, for all of our electrophilic aromatic substitution reactions, we're going to follow a very similar reaction mechanism. So we're going to start with our aromatic ring. I'm showing the simplest example here of benzene, although we will look at more complicated aromatic compounds as well later. So of course, our aromatic ring in this case is going to use its electron donating capabilities in order to donate electrons to our electrophile in this reaction. So we're going to be bringing in some kind of electrophile, which I'll mark as E. So of course, in our nitration reaction, we saw that this was our nitronium ion, but that the exact electrophile will vary depending on what electrophilic aromatic substitution reaction we're doing. The first step is always going to be our ring attacking that electrophile. So this will usually be positively charged, right? So we're donating extra electrons to something that's positively charged. Ring acts as the nucleophile. We attack that electrophile. We end up with this unstable intermediate where we have our rhenium cation forming. So we used up our double bond, we bonded on our new electrophile, and we have our positive charge here inside of our ring. We also at this point have lost our aromaticity, right, because we don't have our alternating double bonds within the ring anymore. We also have a sp3 hybridized carbon here. So this is going to be our rate limiting step. And then from here, we want to eliminate our hydrogen in order to restore aromaticity. So we're going to take the electrons from our hydrogen and we'll dump those in to make a new double bond. You can have whatever weak base is available to pulling off that hydrogen. That could be water or chloride ion if we're forming that hydrochloric acid in our Friedel-Crafts alkylation reaction. And that will take us to our product. So that puts our double bond back. Of course, now our electrophile is on the ring, and our hydrogen, which also kind of acts as an electrophile here, is released as the H+ ion. So of course, this is an electrophilic aromatic substitution because we're taking one electrophile and we are replacing it for another electrophile of our hydrogen. At the end of our reaction here, of course, we've restored our aromaticity. And so we are back to having that stable resonance energy within our aromatic ring. Now we can take this general electrophilic aromatic substitution mechanism and apply it for many different specific electrophilic aromatic substitution reactions. So starting first with the nitration reaction that we've already examined in detail. So again, if we start with our benzene ring, we're going to be reacting with our active electrophile in this case is the nitronium ion, which of course, as we know, is generated using that mixture of nitric acid and our sulfuric acid. This nitronium ion has that positively charged nitrogen that's acting as our electrophile, so our ring is going to be attacking that nitrogen. We substitute that on, and we produce our nitro-substituted benzene, our nitrobenzene. Of course, we're also releasing our hydrogen here, so that gets picked up by the water in our aqueous reaction, and we're producing acid as our secondary product here. So again, our electrophile is the nitronium ion, and we're substituting it for our hydrogen here on the ring that's getting replaced by that nitro group. The central component of our reaction here is that we do need a very strong electrophile, or Lewis acid, in order to take the electrons from our benzene ring to create that product. Right? This is always going to be our rate-limiting step because we're temporarily losing that aromaticity. So we need something that really needs those electrons in order to drive this reaction forward. So we can produce these strong electrophiles using a variety of different mechanisms leading to different electrophilic aromatic substitution reactions. Our next example is sulfonation. So here we're again going to be using a strong Bronsted acid in order to generate that Lewis acid electrophile that we're going to be reacting with our benzene ring. So we again have our benzene ring. Again, of course, this can be other aromatic compounds. Benzene is just the easiest example here. And we're going to react it with sulfuric acid. And when our sulfuric acid loses water, similar to our nitric acid, so if we eliminate water from our sulfuric acid, we can make sulfur trioxide, where our sulfur is going to have a positive charge and will again act as that great electrophile in this electrophilic aromatic substitution reaction. So we end up producing this benzene sulfonic acid, where we have our benzene ring with our sulfur attached. So there's our sulfur trioxide with our extra hydrogen there as we eliminate our, so we actually eliminate the hydrogen from the ring and then protonate this with our extra acid catalyst to get our final product here. Now, one of the previous reactions that we've seen with electrophiles was actually when we had our alkene attacking an electrophile in essentially an electrophilic addition reaction. So of course one of the examples of that is halogenation of alkenes, where our alkene attacks our somewhat electrophilic halogen in our molecular halogen compound. So we can do a similar thing with our benzene ring, although in this case we're going to need to strengthen the electrophilic nature of our halogen. So we're going to react it with our halogens, such as Br2. You could also use chlorine here as well. But we're going to use an iron bromine compound, or an iron halogen compound. You could also do this with chlorine again, in order to increase the electrophilic nature of that bromine. So the products here will be our benzene, of course, our bromine rather, substituting onto our benzene. And we'll have the hydrogen joining together with our bromine to form our hydrogen halide, right? So this hydrogen takes one of the bromines and the other bromine goes on our ring. Our iron bromine compound is just acting as that catalyst. So in order to understand what's going on here, let's take a closer look at our catalyst. So we're going to have this iron bonded onto our bromines, and we're actually going to take our diatomic bromine, and this is going to attach to our iron compound, right? So this iron is going to be relatively positive in our mixture here. So if we attack that with our bromine, we end up getting this compound where we have our two bromines linked together. With positive charge, and our iron is actually going to have excess electrons now. So now at this point, our bromine really wants those extra electrons. So this is going to act as a leaving group, and we're going to bring in extra electrons from our benzene ring. So if I show my benzene ring down here, what we can do is attack this bromine with our electron donation from the ring and break this off as a leaving group so that we can give extra electrons to our bromine here. So at that point then we have our rhenium cation intermediate again, where we have our bromine added on but we still have our hydrogen present. We've lost our aromaticity. We'll have a FeBr4 compound here. So we have the extra bromine and our negative charge here. We're going to give our electrons to our bromine, have our bromine come in and take that hydrogen, break this bond, and of course that will take us to our products. So we get our HBr and our bromobenzene. So again, following the same basic pattern, right? We attack our electrophile, we get this unstable rhenium cation intermediate, we remove our hydrogen, and we form our product here as we restore our aromaticity. In this case, we're just using, again, a slightly different looking strong electrophile that we formed from the combination of our iron bromide complex with our diatomic bromine. And again, you can repeat the same reaction, replacing chlorine instead of bromine, and do the exact same kind of halogenation reaction. As you were looking at that halogenation reaction, you might have noticed that the iron bromide complex that we used there looked very similar to the aluminum chloride complex that I showed you at the beginning of this lecture for the Friedel-Crafts alkylation reaction. Right? So we have the same kind of structure where we have a metal, aluminum, attached to 3 halogens, and this then being used as the catalyst for that particular reaction. So in our Friedel-Crafts reaction, we're going to take our benzene ring again, of course, and we're going to react it with a alkyl halide. So I'm going to use a T-butyl chloride in this case, and we're going to use our aluminum chloride catalyst here, and we end up substituting on the carbon component of my alkyl halide. So I get my 4 carbons here, adding on a little T-butyl group, and of course my hydrogen is breaking off and pairing with my chloride ion from that alkyl halide. So again, of course, that produces that hydrogen halide that can have dangerous fumes there. And of course, in the original reaction I showed, I had just methyl chloride to produce toluene. In this case, we have T-butyl chloride producing my T-butyl benzene. So my reaction mechanism is going to look very similar to that halogenation reaction, right? My aluminum chloride complex is going to help make my chlorine a good leaving group. So what happens here is we take our T-butyl chloride and we're going to give our electrons here to our aluminum chloride because that aluminum it has very low electronegativity, so it's relatively electron deficient in my chloride compound. And when I do that, I again create my chloride, who's now electron deficient with a positive charge attached to my aluminum chloride complex. And so this again acts as a very good leaving group. So I've got my leaving group set up right here. And of course, what we might remember from last semester is that when we have good leaving groups, right, they can pop off and we can make carbocations. Now, of course, a carbocation itself is a very good electrophile, right? This is the very strong electrophile that we used in our nucleophilic substitution reactions in our first semester of organic chemistry. So we have this strong electrophile, which of course is our main requirement for this electrophilic aromatic substitution reaction. So now at this point we can take our ring, and again we can attack that strong electrophile. That produces our uranium cation intermediate. All right, so we add on a new group. At this point we still have our hydrogen attached. And we have our positive charge now in the ring. And now, of course, we can take our aluminum chloride complex and we can pull off our hydrogen in exactly the same way as we did in our halogenation reaction. So I can take the electrons from my chlorine, pull off that hydrogen, break up my aluminum chloride complex, reform my aromatic ring, and I produce my products. So what we see here is that our aluminum chloride complex is acting as a convenient way to produce our strong carbocation electrophile. But as we saw last semester, we can also create electrophiles using other methods as well. So what we see here is we're using our aluminum chloride complex as a convenient way to produce our strong electrophile carbocation from our initial alkyl halide. We can do this with our chlorine-based alkyl halides as well as our bromine-based alkyl halides. Our end goal is just always to get that carbocation intermediate. Now, of course, last semester we saw many other ways to make carbocations as well. And it turns out we can apply those here as well. So if we start with an alcohol here instead, in the presence of a strong acid, so as we know we can protonate alcohols with strong acids. That produces our alkyloxonium ion, where now we have our good leaving group here of our water molecule. So this can break off and form a carbocation, which can then be used in our electrophilic aromatic substitution reaction in the same way as that carbocation produced with our aluminum chloride complex. Now, one of the things we should notice here immediately is that this is a primary carbocation, which is very unstable. So in this case, we will have a rearrangement here from our tertiary carbon here to create our tertiary carbocation. So our Friedel-Crafts alkylation reactions do always include that carbocation intermediate, so we should always be aware of potential rearrangements here. In this case, after we rearrange, we actually create the same exact carbocation that we created with our T-butyl chloride, and so our reaction will actually produce the same product in the end. So we add on our carbons there from our T-butyl carbocation, and then of course we use our water in this case as our weak base to pull off that hydrogen and restore our aromaticity. So pull that off. We're regenerating our acid catalyst, and of course we're adding on our T-butyl group just as we did with our T-butyl chloride. So any different mechanism that we can use to generate that strong carbocation electrophile can be used in this Friedel-Crafts alkylation reaction. Right? We commonly use that aluminum chloride complex just because it is very good at creating carbocations from our alkyl halides, but you can use alkenes with acid, you can use alcohols with acid. As long as you get to a carbocation intermediate, you can always use that as your electrophile in this Friedel-Crafts alkylation reaction. The final reaction that we're going to look at today is our Friedel-Crafts acylation reaction. So as the name suggests, we are going to share a lot of similarities with our Friedel-Crafts alkylation, but we're slightly changing up what group we're going to be adding onto our benzene ring. So we again start with our benzene, but now we're going to be adding a acyl halide. So we have our chlorine attached to a carbon chain with our carbonyl carbon double bonded to oxygen here, instead of just our simple carbon structure. So we call this a acyl halide, or acyl chloride specifically. And of course, we're also going to use our aluminum chloride-based complex in order to help with this reaction. The end result is going to be our new substituted benzene ring. In this case, we're adding on our carbonyl, carbon-oxygen double bond, in addition to that carbon structure, and we're again going to get our hydrogen halide byproduct. So our reaction here will look very similar. So what we're going to be doing again is taking that aluminum chloride complex and using it to create a good leaving group from our chlorine here. So we attack our aluminum chloride. That gives us our good leaving group. And this will then break off, but instead of forming a carbocation, we're going to form a slightly different electrophile here. So this breaks off, and we're actually going to take the extra electrons from our oxygen and bring them down at the same time. And so we get this structure here, which we call an acylium ion. So our oxygen takes the positive charge, although we actually have resonance structures here where we can share that positive charge between our oxygen and our carbon. So we can have some positive charge on the carbon, some positive charge on the oxygen. This will be the major resonance structure because we have both of our atoms here with a full octet. So this again will just act as our strong electrophile, and we can attack with our electron donating benzene ring in the same way as we saw before. So we attack our carbon, and we're going to give our extra electrons back to the oxygen using our acylium ion intermediate here. That will result in our new compound being added on here. our double bonded oxygen. We're still going to have our hydrogen here and our acylium ion intermediate. And of course, just as before, our aluminum chloride complex will break up in order to form our restore our aromaticity and form our final product. So there we have it. Again, following a very similar mechanism to our Friedel-Crafts alkylation, but instead of using our typical carbocation, we have our slightly different electrophile here of our acylium ion. Again, we have the similarity in names of these two different reactions, both because of their similar mechanisms, as well as the fact that they're both discovered by that combo of James Craft and Charles Friedel, who had that great chemistry partnership in the 1800s. Now, all these different electrophilic aromatic substitution reactions allow us to modify our aromatic rings in many different ways to create a wide range of different compounds. So they're very valuable for allowing us to synthesize different compounds containing that aromatic ring. Right? We can just start with benzene, and you can see we can get a wide range of different products depending on what electrophilic aromatic substitution reactions we use. Now, of course, once we start to add groups onto our ring, our reactions from here are going to get more complicated, right? Because as we've seen, our groups will affect each other in terms of their reactivity, right? Electronegative groups pull electron density towards them, or you can have electron donating groups that might be able to give you extra electrons, and those will both alter that reactivity. So that's what we'll look at in a future lecture.